Okay, howdy guys. We're going to be investigating a bunch of different laws, and I call them the ABCs of the gas laws because it's Avogadro's, Boyle's, and Charles' ABC. And then but don't forget about Dalton's law. You learned about Dalton's law a little earlier, so it's going to be ABCDs, and we'll also learn about the G's as well, Gay-Lussac's law. So we'll just call them the ABCs for now. Uh, the first one is Avogadro's law, and it is relating to the pressure and the amount of gas. So we're going to increase the amount of gas in this balloon, and I want you to really look at the pressure. Don't focus too much on the volume. As I blow air into this balloon, what is going to happen to the pressure inside of it? All right, you can see that there is pressure on the inside that is pushing on the outside, and it pushed the balloon out. And if I add even more air, I will increase the number of particles, which will increase the collisions, which will increase uh, uh, which will actually end up increasing the volume. So you see an increase in volume, but there is initially an increase in pressure. We're going to show this graphically right here, and it's going to be awesome. What we're going to do is we are going to take our gas pressure sensor and our syringe, and we are going to um, squish it all the way in, attach it, and then pull it back to 5 milliliters. That's actually really hard because that should be a vacuum. It should be no air in there. And we're going to take a reading. So it should be no air, no pressure. And then we're going to unplug it. We're going to pull it back to 1 milliliter and then reattach it. So we have 1 milliliter of air in here, and we're still going to pull it back to 5 milliliters and then take another reading. Okay, so there's still 1 milliliter of air, but taking up 5 milliliters of space. And then, hopefully you got this. We're going to pull it back to 2 milliliters, reattach it, and then we are going to pull it back out to 5 milliliters. So now there are 2 milliliters of air taking up 5 milliliters of space. So it should have an increase in pressure, right? Okay, check it out. So we're going to start at no moles of air, and so that's what the pressure would be with no moles of air but 5 liters of volume. And then we're going to unplug it. We're going to set it at 1 milliliter, 1 unit of air, but 5 milliliters of volume. We'll set it at 2. And hold on. Okay. Now let's set it at 3. And this is 4 milliliters of air with 5 milliliters of volume. And just for grins, let's go ahead and do 5 milliliters of air, 5 milliliters of volume. This should be our atmospheric pressure. Now let's take a look at what these laws look like on paper. So we're going to look at the picture perfect way a graph should look like. So for pressure and the amount of gas. So this is sometimes called moles, or right now we're just thinking of it as units of air, right? At the moment. But you can call it moles, which is the number of particles. So this is called Avogadro's law, and that's the equation for it. I'll get back to this one in a second. But if we take a look uh, at the graph, we have pressure on the y-axis and then the amount of gas on the x-axis. So that is in gas units. I don't actually have the units here. This is just a sketch. There's no
numbers here, we're just showing the general trend. And as we can see that as we increase the amount of gas, we will increase the pressure. That makes sense because if we pressure is the force over the area, right? So if we are increasing the amount of gas, we are increasing the number of collisions, which is increasing the number of force. So we're increasing the collisions. And that's what's going on. We're going to increase the collisions, which is going to increase the pressure. Now, this relationship right here, where it's a straight line, is called a direct relationship. Uh, so let me show you what that means. So this is a direct relationship and it's a linear relationship. Now, what that means is if you have an initial condition here, so this would be your initial, and this is your final condition over on the right. So that's what the subscripts mean. And one just means the first condition, two means the second condition. So if we double um, the number of moles or the number of gas units, we are going to double the pressure. Okay, to make this to make that fraction work. So that's what Avogadro's law is.
Okay guys, so we're going to show you Boyle's law, and a quick demonstration of this is just using a syringe. Boyle's law is measuring pressure and volume. We're going to keep the temperature, and we're going to keep the number of moles, or the number of air particles, the same. So we're going to show you a syringe with a marshmallow. And so we'll put the marshmallow in there, and we'll close up the syringe. Now it's got the air that's inside it, a little bit more than 20 milliliters. We're going to put our finger on the top, and we're going to watch the marshmallow here whenever we push it in. See what happens to the marshmallow. It shrinks. Looks kind of cool because it gets tiny. What happens is those air particles or air bubbles that are inside of the marshmallow get compressed down, and so that's what happens. You see all of a sudden it gets a little bit higher. Now hold on a second. Let me show you a reverse. So I'm gonna, without my finger on the button, I'm gonna push it in until I don't want to get it stuck in there. Now let's see what we can do when we pull the plunger out. Oh wow, look at that. The marshmallow gets a lot bigger. Alright, that's because all those air bubbles, pockets of air inside the marshmallow start to expand. So let me show you exactly what is going on here. If we actually push, if I just push my finger on here, you can figure out that I can able to push it down, but I'm not able to compress it all the way. I'm compressing those air particles, but I'm not able to get it all the way through. The pressure increases as I decrease the volume. Watch that again. I'm going to decrease the volume. I'm going to increase the pressure. I can really feel that pressure. You could probably even feel it with me. So I'm going to show you graphically how this works. We're going to take a pressure sensor and then take this syringe. We're going to plug it right on here. And what we're going to do is we're just going to start at 20 milliliters, and we're going to increase it by 1 milliliter at a time and see how the pressure changes. So let's start there. We'll start at 20 milliliters, and then we'll increase to 19, then we'll increase to 18, and then increase to 17, increase to 16, increase to 15, 14, 13, 12, 11, 10, 9, and we're going to max out the pressure sensor at 8 milliliters. So that's why you're going to see a very slight bend, and you see a break in the trend. So check that out.
Boyle's law is deals with pressure and volume. So we're going to take a look at this and just look at what the graph, perfect graph would look like. So you would see something like this if you plotted pressure versus the volume. Now you notice that it's not a straight line, and it makes this asymptotic relationship right here. The line will move all the way close to the x-axis and approach zero but never touch it. And the line will approach here but never touch it. So if you take that syringe and if you press it down, and if you try to decrease the volume as much as possible, you're going to increase the pressure, and it's going to get harder and harder. It's going to get really hard, but you will never be able to get the syringe to touch the actual y-axis, okay? Or you never be able to get the pressure to be zero. So this is not a straight line, so it's not linear, okay? So we can manipulate our data to make it linear. Watch me do this. So if we simply just take 1 divided by the volume and put it on the x-axis, this is what we're going to get. So if we get pressure on the y-axis, and if we get 1 divided by the volume, well, then we get a straight line. So check that out. That's 1 over v. So another mathematical way to show that is the inverse of v, right? So that's why we call this an inverse relationship, okay? We had to take the inverse of the x-axis to be able to get that. So hopefully that makes sense. Now what that is saying, that as volume is doubling, if we double the volume, let's take a, let me rewrite that. Pressure equals 1 over V. So if we double that volume right here, we are going to take this and multiply it by a half, all right? So you're going to cut the pressure in half. And so that's what's essentially going to be going on here. So if you increase the pressure, you're going to decrease the volume. And so this is the only one that has that opposite effect, all right? And this is the only one that is an inverse relationship. So we call Boyle's law, the equation for that is going to be P1V1 equals P2V2. So there's your initial condition on the left and your final condition on the right. So if you know your initial pressure and your initial volume and you change it to a new pressure, you will be able to calculate the new volume.
Okay, so the next law is going to be Gay-Lussac's law. Now this is with pressure and with temperature. So we're going to take something that's really cold and this little bottle and has just a little bit of water on the inside. We're going to wet our finger on the top just to get it nice and wet on the top. And then we're going to put a penny and get it nice and cold, an ice cold penny right on top. Now that it's there, we're going to try to increase the temperature of that bottle. If I rub my hands together, try to get them a little bit warmer, and I'm going to grab it and watch what happens to the pressure. Okay. Very miraculous there. You can see the penny move a little bit. That's because it increased the frequency of collisions of the gas molecules, so that gas was able to push out and push the penny out. Now we've actually have a little bit, oh, it even bumped it just a little bit more. So let's see if we can try it one more time. There it goes. It's like Old Faithful, right? So this is to graphically show this, we're going to do a little experiment here where we have some warm water. It's about 60 degrees Celsius. Not too hot, but kind of hot. And so we're going to have a pressure sensor here on this test tube, and we're measuring the temperature as well with the thermometer. So now once that's done, we're able to measure the pressure as it heats up. So we're going to increase the temperature, and so we should see an increase in pressure. So we're going to take a look at our data collected from our real sample of Gay-Lussac's law. So all I did was had that change the temperature of my boiling water, and then I measured the pressure of that test tube that was inside the boiling water. So that was the same temperature as the water. That we were able to assume that. So we started at about 60 degrees Celsius, and then so as it increased, we got to around the boiling point. We didn't go higher than the boiling point. That's not possible because you would have a gas instead. You would not have boiling water. You'd have a gas. This doesn't tell you much, but it does tell you that it's a straight line. Okay. So after that, let's see if we can change this temperature scale. This temperature scale is degrees Celsius. Well, it's better if we look at it in degrees Kelvin. So if we check this out, I'm going to change the scale of this to include absolute zero. So to go all the way down to negative 273 degrees Celsius. So I'm going to include negative 300. And so when I look at that, the slope of this is going to trend down this way, and it's going to get to around 273 Kelvin, and that's going to be how it works. That's pretty amazing, right? So that makes sense, though. If you slow the temperature down enough, you would get something that was around zero pressure. Awesome.
Now, our relationship between pressure and temperature is a cool one. So now we actually, and cool literally, because we get to see temperature right here. And we're going to see pressure on the y-axis and temperature on the x-axis. Now, this is called Gay-Lussac's law. It's a French name, so that's pronounced Guy. So what happens here is that temperature is in a special unit called Kelvin. Remember, there's no negative Kelvin, so it approaches zero, and then zero Kelvin is absolute zero. Now, that means that 0 Kelvin is when the kinetic energy is 0. Okay, that means that the molecules have actually just stopped and they're not moving anymore. That can't actually happen. So when we see our line here, we're going to draw an open point right here, which means that it does not include actually 0. It gets close to it, but cannot actually happen. So as you see that this guy is a direct relationship, because if we just plot the two of them, we get a linear straight line. And so that means that if we double the temperature, then we will double the pressure. Okay? If we increase the temperature, we will increase the pressure. That's what that's saying. Increase the temperature, we will increase the pressure. So we have this as P1 over T1 equals P2 over T2. Now here's another reason why we do this in Kelvin, is because Kelvin is always greater than 0, right? There's no negative Kelvin numbers, and you can never actually get to 0, because if 0 is here, then you'd be dividing by 0 and breaking the world, right? So that doesn't work. So that's why we always put our temperatures in Kelvin. You can have 0 degrees Celsius, but you can never have 0 Kelvin. Okay, so that's another reason mathematically why when you plug this in, you always use Kelvin.
All right, the last one we're going to show you is Charles' law, which is a relationship between temperature and volume. Hopefully as the temperature will increase, that's actually going to increase the collisions with the container. And so if it's a flexible container like a balloon, then it is going to expand. So here is something at room temperature. I'm just holding it right now, just as a reference point for what you see. And then if you look here, we have something that's being heated up. And so you can see that the particles are increasing their speed and the frequency of collisions. So they're colliding with the balloon a little bit more and spreading it out more. Now if we zoom back over here and we come over to the ice cold one, we can see that the volume has actually kind of shriveled up just a little bit, and so the volume has decreased just a little bit. So we'll see that temperature is dependent on volume.
Now the paper translation for volume and temperature is going to look like this, and this is what we call Charles' law. So we have volume on the y-axis and then temperature on the x-axis. So temperature is going to be an open point right here because remember that 0 Kelvin is not actually possible. But as we increase the temperature, we're going to increase the volume. Okay? And we will increase the volume, which leads us to believe that we have a similar type of equation. We have V1 over T1 equals B2 over T2. Now remember, temperature must always be in Kelvin. And as you can tell, this is a linear relationship, which is just a direct relationship. So if we double our temperature, we will double our volume. Pretty simple. So that's the way direct relationships work. If you double the temperature, you double the volume. All right. Have a good day. Have a great day.